welcome to lesson 5.2 on probability. Probability rules! Alright, and we'll discuss some probability rules. The sample space, S, of a chance process is a set of all possible outcomes. So that means if you're rolling a die, it's values 1, 2, 3, 4, 5, 6 that make up the sample space. A probability model is a description of some chance process that consists of two parts, a sample space, and the probability of each outcome. This is usually in a table. An event is any collection of outcomes from some chance process. That is, an event is a subset of the sample space, usually denoted with a capital letter. R is rain in October in Spring Grove. The probability of R is 99% chance that we're going to get rain in October in Spring Grove. Imagine flipping a coin 3 times. Describe the probability model for this chance process and use it to find the probability of getting at least one head in 3 flips. So the probability model includes both parts, the sample space, which is every possible outcome, and each of their probabilities. So the sample space, I'm going to start and organize and be systematic so that I don't forget or miss one of the options. So 3 heads, 2 heads with a tail in the end, with a tail in the center, and with 1 tail in the front. So far I've done no tails and 1 tail. Here's my 2 tail options, 2 tails on the ends, a tail on either end, and 2 tails in the front, and then 3 tails. Okay, and the probability of 1/8 for all those situations, because each of them have equally likely probability of happening. And then find the probability of getting at least one head in 3 flips. So this would be the probability of getting at least one head, which is this event, this event, this event, 2 head events, and the 3 head event. So it'd be 7 of the 8 probabilities. Or add them up, 1, 2, 3, 4, 5, 6, 7 of the 8. All right, and then let me get that decimal for you. 0.875. Summarize the 5 basic probability rules. Any event A is, for the probability of A, it's somewhere between 0 and 1, inclusive, meaning it can be 0, it can be 1, or it can be anything in between. Just be careful of scientific notation, though. I went over this in the chapter before, or lesson before, that if you get 3.24, that you really don't have a 325% chance of something happening. It is times 10 to the negative 9. It's a really, really, really small chance of something happening. So make sure that you write it out in scientific notation then. Okay, if S is the sample space, then the probability of all the events in the sample space equals 1. So therefore, all probabilities in the sample space add to 1. So there are all these probabilities here add to 1. Okay. In the case of equally likely outcomes, you can do something like this. The probability of event A is the number of outcomes corresponding to A over the total number of outcomes in the sample space. So die, coin flips, drawing a card, each of these things tend to represent equally likely outcomes. It's just like the one we did up above here, where 7 of these 8 events in the sample space were all events that we were considering a success. So we had 7 out of 8 for our probability. Let's see here. Okay. The complement rule says that the probability of A complement is the same as the probability of not A, and that's 1 minus the probability of A. So the probability of A not happening is 1 minus the probability of A happening. All right, the general addition rule says that for the probability of A union B, union means the same as or and means the same as a plus sign in this probability notation. So or would be a union or a plus sign, and so the probability of A plus B would be the probability of A plus the probability of B minus their intersection in case there's a set area where A and B occur together. So let's look at this example, the probability of blue eyes or female. Let's check out this table. Okay, so what we should do is we should add up all the blue-eyed individuals, which is 11. Add up all the females, which is 10, but then when I add up 11 and when I add up 10, I have added this square in these to make 11 and in these to make 10. So I've counted this square twice. So I have to be careful to subtract the 7 that I counted twice. And I get 14 out of 19. What does it mean if two events are mutually exclusive? It means that they have no events in it means that they have no outcomes in common, so they can never happen together. So if you think of driving to school or walking to school, you have those two options. We tend not to do both. So if you drove to school today, then you drove, and if you walked, then you walked. Okay. An example of mutually exclusive events is having a dog and having no pets. No one can be in both camps at once. You either have a dog or you have no pets or some other combination. Okay. But these two are mutually exclusive in that they can't happen together. So raise your hand if event A is true for you. Raise your hand if event B is true for you. And then see how mutually exclusive works. Nobody was in both pets camps. Okay, and example of not mutually exclusive is an example of being female and the outcome of a senior. So raise your hand if event A is true for you. Raise your hand if event B is true for you. See how many of you females kept your hand up for senior. So you reside in both events. So these two events are not mutually exclusive. Okay, so let's talk about two more events. Your mother works and your mother doesn't work. Okay, if I was to make Venn diagrams and count the students in the class, I could count maybe 16 students whose mothers work and 3 students whose mothers don't work, but these are mutually exclusive events. This 0 in the middle is really there because there will never be any mothers that work and don't work, okay? So they are inherently opposite of each other, and there would be no mutually exclusive. They are mutually exclusive. There would be nothing in the intersection ever. Okay, the intersection of works and doesn't work is 0. Okay, therefore they are mutually exclusive. The probability they do both is 0. Randomly select a student who took the 2016 AP Statistics exam and recorded the student's score. Here's the probability model. Show that this is a legitimate probability model. That's a great question that appears over and over. We have to do 2 tasks. We have to prove that each probability is between 0 and 1, and that all the probabilities add to 1. So each probability, is it less than 1 but greater than 0? Yep. And do all the probabilities add to 1? Yes. You must directly address both of those characteristics in word form, not just showing this alone, because you have to describe to the grader what it is that you're trying to prove. Okay, so describe that each value is between 0 and 1, and describe in words that all the probabilities add to 1. Then it is important that you still do show this, though, to make sure that you are showing the evidence. Okay, find the probability that the chosen student scored 3 or better. This is often called passing the AP Statistics exam. So we add up 3, 4, and 5, the probability of getting a 3, a 4, or a 5, and we get 0.933. Or you can subtract the probability of getting a 1 or a 2 from the value 1. Okay? Now this is a great example of mutually exclusive events where each happens on its own and there's no intersection. So if somebody got a 4, they didn't get really like a 4 or 5, they got a 4. So therefore, when I add up the probabilities, I can add up and I don't need to worry about subtracting the intersection. Okay. Students in college statistics class wanted to find out how common it is for young adults to have tattoos. They recorded data on 2 variables, gender and whether the student has a tattoo, for all 178 people in the class. The two-way table displays the data. Suppose we choose a student from the class at random. Find the probability that the student has a tattoo. All those that have a tattoo is 103 out of 178, and that's 0.579. If the question asks you for a probability, leave it in probability format, a value between 0 and 1 inclusive. Is a male and has a tattoo. Male and tattoo is these 19 out of 178. Is a male or has a tattoo. So I have 90 males and I have 103 tattoos and 178, but it counts 19 twice. So another thing I can do is because this whole table is so small, it's only like 2 by 2, then you can really just count up all the successes. So male, male, and tattoo counts all the tattoos. So if you add up 90 for all the males and 84 additionally for having a tattoo, then you can add up a little bit quicker. 174 over 178 is 0.978. Okay, so here's a general addition rule for mutually exclusive events. It just is missing the subtraction of the intersection at the end. Just add up all the probabilities and that's it. How are the union and intersection symbols used? Union is for or a plus sign. Intersection is for and a multiplication sign. Who owns a home? What is the relationship between educational achievement and home ownership? A random sample of 500 people who participated in the 2000 census were chosen. Each member of the sample was identified as a high school graduate or not, and as a homeowner or not. Overall, 340 were homeowners, 310 were high school graduates, and 221 were both homeowners and high school graduates. So the first thing I'm going to do is I'm going to put my variables down: high school grad, not high school grad, homeowner, not homeowner, and then another column for total. I know I have 500 people total, and they told me that 340 people were homeowners. That goes all the way in the total homeowners. 310 were high school grads, and 221 is in the intersection. So that gives me enough to make a subtraction to get 119, to make a subtraction to get 89, to make a subtraction to get 190, to make a subtraction to get 160, and then to make a subtraction to get your 71. Suppose we chose a member from this sample at random. Find the probability the member is a high school graduate. Show your work. So if they're a high school graduate, it'd be the 310 out of 500. Is a high school graduate who owns a home. High school graduate homeowner is 221 out of 500. And is a high school graduate or owns a home, so we can take high school grad, homeowner, minus the intersection. And so that was high school graduate, homeowner, minus the intersection out of 500, which is 429 out of 500, which is 0.858. All right, phone usage. According to the National Center for Health Statistics, in December 2012, 60% of households had a traditional landline phone, so landline 60%, 89% of households had cell phones, so cell phone 89%, and 51% had both. Suppose we randomly selected a household in 2012, make a two-way table that describes a sample space, so we can subtract to get the value, subtract to get the value, subtract, and then finally subtract. Find the probability that the household has at least one of the two types of phones. So at least one is 1 minus the probability of none, and no cell phone and no landline is this 0.02 group. So we could take 1 minus 0.02 and get the 98% of the households. Find the probability the household has neither type of phone, and discuss at least one is none. Okay. The probability of none is 0.02, and that's the same as cell phone complement and landline complement. So it's the same thing as no cell phone and no landline. Okay, so that would just be the intersection of those two things. Find the probability, so that means that I can just take the 0.02 square right from the cell here, because no cell and no landline is right there, 0.02. Okay, find the probability the household has a cell phone only. So cell phone only would be here with cell phone and no landline. Okay, so that would be 0.38. And I just showed some notation using cell phone and no landline. Okay, at a community swimming pool, there are 2 managers, 8 lifeguards, 3 concession stand clerks, 2 maintenance people. If a person is selected at random, find the probability that the person is either a lifeguard or a manager. So or is a plus sign, so lifeguard or manager is 10 total people out of 15. At a convention, there are all these people: 7 math, 5 computer science, 3 statistics, and 4 science. If an instructor is selected at random, find the probability of selecting a math or a science. So there are 11. Okay, so then Netflix is acquiring the following number of movie titles in each of the categories: 170 horror, 230 drama, mystery, romance, comedies. If a person watched one of the movies at random, find the probability of a romance or a comedy was rented. So we have 460 or 0.47. Okay, thanks for joining.